Hello and welcome. In this video, we are going to look at some analytical ways to evaluate a limit in circumstances where direct substitution does not necessarily work. We are also going to talk about different properties of limits. Just like in Algebra 1, you talk about the commutative property, the associative property. We're going to talk about different properties of limits and how that can help us evaluate a limit as well. But before we jump into looking at those limit properties and before we jump into different strategies for evaluating limits analytically, let's just refresh on evaluating a limit using direct substitution. So I encourage you, if this is something that you're already familiar with, to pause the video and work through each of these 6 sort of warm-up problems and then unpause the video and see how you did. So when I look at number 1, I know that this is just a quadratic function here that I'm evaluating the limit of. So I can just use direct substitution and plug 2 in each place that there is an x. So here, that would give me 2 squared plus 4 times 2 plus 1, or 4 plus 8 plus 1, which is going to be 13. On number 2, there is an x value that would not allow me to use direct substitution, and that would be when x is equal to 3. But since I'm finding the limit at x equals 2, I can just use direct substitution. We just did the direct substitution part for the numerator over here. So I'm going to just note that the numerator is 13 when we plug in 2. And the denominator, 2 minus 3, is -1. So this is going to give us -13, the limit as x approaches 2. Now on number 3, what I want you to notice is that this denominator will not allow me to directly substitute 2 in, because if I substituted 2 into the denominator, I would get 0. And in fact, also, if I substituted 2 into the numerator, 2 to the 4th is 16 minus 16 is 0. So if I tried to use direct substitution here, this would give me 0 over 0, which is not a thing that we're allowed to get. It's actually something that has a special name, and we're going to come back to number 3 later in this lesson after we talk about some other strategies. Number 4, if I substitute 30 in, I get the square root of 30 minus 5, or the square root of 25, which is 5. On number 5, if I substitute 5 in, I get 5 to the 3rd, or 125 over 7. And on number 6, if I directly substitute -1 in, I would get -2 minus 1, or -3 to the 3rd, which would be -27. So one of our main goals in this lesson is to talk about how we could evaluate a problem like number 3, or how we could try and reformat it so that we maybe could. But before we jump into that part, let's go ahead and talk about the algebraic limit properties. Something really important to note about these properties is this if portion at the beginning. In order for us to use any of these 6 properties, it must be the case that the limit as x approaches c of f of x exists, that it's some number L, and that the limit as x approaches c of some g of x is a number m. So we're talking about limits that exist. If one of these limits don't exist, then we can't use these properties the way that they are described below. So the first property says basically that if we're taking the limit of 2 functions that are being added together, we could look at their limits as 2 separate pieces. So if I had the limit as x approaches 2 of 6x squared plus 2x, I could actually look at this as 2 separate limits, the limit as x approaches 2 of 6x squared, and the limit as x approaches 2 of 2x. Now, in this circumstance that I just created, it would not necessarily make sense or make this problem any easier to separate it, but there are other circumstances where separating it could actually help us out. Property number 2 is the exact same thing except with subtraction, so I could go back to each of these pluses, and I could turn them into subtraction. I could find the limit of each of these 2 functions separately and subtract those 2 limits. The third property says that if we have some scalar or some number being multiplied by our function, some k value, we could actually just find the limit first and then multiply the k value afterwards. So for example, if we had the limit as x approaches 2 of 2 times sine of x, we could actually take that 2 in front, which in some circumstances could make it easier for us to find the limit, and then multiply it by 2 afterwards. The fourth and fifth properties talk about multiplication and division. So if we're multiplying two functions or dividing them, and when we divide, we need to make sure that we're not changing this so that we're dividing by 0, which would not be okay. But we are allowed to split things up in that way. So if I had the limit as x approaches 2 of x plus 2 times x squared plus 4, I could split that into the limit as x approaches 2 of x plus 2 times the limit as x approaches 2 of x squared plus 4. Or similarly with division, if I was dividing the limit as x approaches 2 of x plus 2 over x plus 4, I could split this into two limits, the limit as x approaches 2 of x plus 2 divided by the limit as x approaches 2 of x plus 4. And those properties allow us to go back and forth in those two ways to help us simplify a limit that may otherwise be a little bit more strenuous. The next one on here says that if we are taking the limit as x approaches c of some function to a power, what we can actually do is we can take the limit and then apply the power afterwards. So if I had the limit as x approaches 2 of x plus 4 squared, I could rewrite that as the limit as x approaches 2 of x plus 4, and I could take the whole limit and raise that to the power of 2. There's one more that's not on here, and it's called the composition property, which basically says that the limit as x approaches some c value of g of f of x. So if we have a function inside of another function, that this is the same thing as g of the limit as x approaches c of f of x. Meaning you would find the limit in terms of f and evaluate that or plug that into the function g. So we'll be looking at that property as well. So those are our 7 basic properties for limits. Now let's look at them in a really basic way and see how we can use them. I just noticed that I had a couple of typos here, so I'm going to fix those really quickly so that we can work through this. Here we go. So for number 1, well, for all 3 of these problems, we are given that the limit as x approaches c of f of x is 2, and the limit as x approaches c of g of x is 12. So notice they're both approaching the same value, c, and we're being asked to determine some other pieces of information. So number 1 is asking us to find the limit as x approaches c of f of x over g of x. Well, based on the property about division, that means that I can actually find each of these limits separately, and those are given. So up here, that limit for f is going to be 2, and down here, that limit for g is going to be 12. So this limit would be equal to 1 over 6. Number 2 says the limit as x approaches c of f of x to the power of 2 over 5. Well, this is the same thing as the limit as x approaches c of f of x, and this limit being raised to the power of 2 over 5. And here's why that helps us. We know that this, or I should use red, this is equal to 2. So now we're saying we have 2 being raised to the power of 2 over 5. So that's going to be 2 squared, or 4, to the power of 1/5. And I'm going to just leave that answer like that. Why don't you go ahead and pause the video and see if you can work through number 3 on your own. And then unpause the video and see how you did. All right, number 3, we can separate this. This is the limit as x approaches c of f of x minus 2 times the limit as x approaches c of g of x. Well, we know that this first limit is 2, minus 2 times, we know the second limit is 12, so this is going to be 2 minus 24, or negative 22. So using those properties of limits often makes a limit that may otherwise be difficult to evaluate just a little bit easier to look at. Or even just something that seems complicated, it might simplify it out a little bit. Let's move on to our next topic. So as we saw in our warm-up, and I'm going to actually rewrite that problem that was on that front page, number 3, the limit as x approaches 2 of x to the fourth over x to the fourth minus 16 over x squared minus 4, sometimes we aren't able to do direct substitution because there's some sort of discontinuity. In this case, the issue is that when we try to use direct substitution, we get 0 over 0. And that actually has a name. It's called indeterminate form. An indeterminate form can also be infinity over infinity or negative infinity over negative infinity. But for right now, we are going to look at indeterminate form when we get 0 over 0. There are 3 basic strategies to help when something like this happens. One of those strategies is factoring. The other one is conjugate, and one we're going to get to in the next video is actually using different trig identities or trig limit properties in order to help us simplify. So the first strategy we're going to focus on is factoring. So what you need to think about when you have a problem that's giving you indeterminate form, first is, can I factor what is here to simplify the limit by creating a new function, which is actually exactly the same as the old function, except at one particular point. But that new function would then have a limit if we use direct substitution. So when I look at number 3, and I see polynomials in the numerator and the denominator, I'm asking myself, well, can I factor anything here? So if I factor the numerator, I have the difference of squares. That's going to give me x squared plus 4 times x squared minus 4. And the denominator, I could factor, but I actually can see already that if I don't factor it, I now have an expression, or I now have a piece of this that could divide out to be 1, because anything divided by itself is 1. So if I factored and divided this out, I would have a new limit where I'm now just looking at x squared plus 4. And I can use direct substitution here. The only difference between this function and this function is that the new one that I have created in red exists when x equals 2, and the original function doesn't exist. So the original function has a hole when x is equal to 2. But as we learned in the previous video, even if there's a hole, the limit can still exist because the function is still approaching the same value from the left and the right. So now that I have this new simplified function, I can use direct substitution to get 2 squared plus 4, which would give me 8. Let's look through some more examples that involve factoring. So anytime you're working through a limit problem, the first thing you should always try and do is use direct substitution, because that is always going to be the fastest method if that works. If it doesn't work, then we're going to look to see if we can factor or if we can use conjugates, which we're going to go over next. So when I look at number 1, my first thing is, what happens if I use direct substitution? Well, if I use direct substitution, I would get 0 in the numerator and the denominator, meaning I have indeterminate form, which is not going to allow me to evaluate this limit. That is the reason that I'm now looking for a new strategy. So let's see if we can factor. Well, the numerator is just x. I can't factor anything there. But the denominator, x squared plus x, that has a greatest common factor. So I can factor an x out, which means now these two x's can divide to be 1. So that gives me the limit as x approaches 0 of 1 over x plus 1. So again, I have created a new function, which is exactly the same, except at the moment that x equals 0, right? I got rid of my issue of having the hole. I can now look at the limit from both sides of this function using direct substitution. That would give me 1 over 0 plus 1, or just 1. I encourage you to pause the video and see if you can do 2 and 3 on your own. Okay, hopefully you've had enough time. The first thing I notice about number 2 is that I can't use direct substitution because I would get indeterminate form. So I'm going to go through and factor the denominator here so that these two factors can divide to be 1, and I'm left with the limit as x approaches 9 of 1 over x plus 9. And if I substitute 9 in, I get 1 over 9 plus 9, or 1 over 18. And then number 3, if I try to use direct substitution, I'm going to get 8 minus 8 in the numerator, which is 0, over 2 minus 2 in the denominator. So I'm going to get indeterminate form. So I'm going to factor the greatest common factor out of the numerator, which is x squared. And I'm going to factor x, I'm going to divide these x minus 2's away. So I have now created a simpler function that does exist at the value, which means I can use direct substitution to get that this limit is going to be 4. So again, your first step should always be to attempt to use direct substitution. If that doesn't work because it results in indeterminate form, then you're going to see if you can factor. But what happens if you can't factor? That leads us to our next approach, which is using conjugates. So in case you have forgotten what a conjugate is, a conjugate has to do with radicals. And it is something, if, for example, I had the square root of x plus 1, the conjugate of that would be the exact same expression except with subtraction in between. And the beautiful thing about conjugates is when you multiply them together, you have the difference of squares. So if I multiply the square root of x times the square root of x, I get x. If I multiply the square root of x times negative 1, I get negative square root x. Then I get positive square root x, then I get negative 1. So this whole thing actually simplifies to just be x minus 1. So if you see a radical in your limit and you have already tried and been unable to use direct substitution, using conjugates is a great strategy to use. So what you will do is multiply both the numerator and the denominator of your fraction by the conjugate, and then simplify and see if you can use direct substitution. One thing I will warn you about on this is that you don't want to multiply too far because that's actually going to make your life a little bit more difficult. So I'm going to actually say don't multiply everything, and I'm going to show you what I mean when we jump into some examples. So the key identifier that tells you that you should attempt to use a conjugate is that you get indeterminate form, 0 over 0, and there's a radical in the problem. Those two things are telling you conjugates are probably going to help you out. So let's look at some examples. Number 4, if I tried to use direct substitution, I would get 0 over 0. So I'm going to multiply the numerator and the denominator by the conjugate, which is going to be the square root of x plus 1. Square root of x plus 1 over the square root of x plus 1. Since I'm multiplying it on the numerator and the denominator, I'm really just multiplying this fraction by 1. Because of the difference of squares and what we just saw on the other side, the numerator is just going to become x minus 1. Now here's where I'm telling you, don't multiply these two things together. Just write them as the product in the denominator. And I'm wondering if right now you can see why. So the reason why is because these two things are going to divide to be 1. And if you multiply them out, you're not going to be able to see that. Because those divide to be 1, this is going to give me the limit as x approaches 1 of 1 over the square root of x plus 1, which I can now use direct substitution on to get 1 over 1 plus 1, or 1/2. I encourage you to pause the video and work through 5 on your own, and then see if you can find a good approach for number 6 as well. Okay, so hopefully you have had time to work through this on your own. I get indeterminate form if I use direct substitution, so I'm going to multiply both the numerator and the denominator by the conjugate, which is going to be the square root of x plus 2 plus 5 over the square root of x plus 2 plus 5. That's going to give me the limit as x approaches 23 of x minus 23. Remember, I'm not actually going to multiply this, times x plus 2 inside the square root, plus 5 over, in the denominator, the square root of x plus 2 times the square root of x plus 2 is x plus 2. Negative 5 times positive 5 is minus 25. So this is going to simplify to be x minus 23 times this radical, or this conjugate, over x minus 23. And those factors are going to divide out to be 1. So the limit as x approaches 23 of the square root of x plus 2 plus 5. This function is equivalent to this function everywhere except at 23, which is the place we want to find the limit of. So we can now use direct substitution. That's going to give me the square root of 25, which is 5 plus 5, which is going to give me 10. Now, number 6 has no radical, and it gives me indeterminate form. So my best guess here is that I can likely use factoring, although many of you have forgotten likely how to factor perfect cubes. So this is going to be x minus 1 times x squared plus x plus 1. And that is going to be divided by x minus 1. If you didn't remember how to factor that, you could always do long division, x cubed minus 1 divided by x minus 1. And that would give you the same result that we're going to get here, which is that this factor divides out. And our equivalent limit is going to be just x squared plus x plus 1, which we can now use direct substitution on to get 1 plus 1, which is going to be 3. So the key ideas in this section. We should always start when looking to evaluate a limit by checking to see if direct substitution works. If it doesn't work, we should look at factoring as an option, factor the numerator and the denominator, and then see if you can use direct substitution after simplifying. If that doesn't work and we see some radicals, we should try using conjugates, multiply the numerator and the denominator by the conjugate, simplify that, and then check to see if you can use direct substitution as well. In the next video, we're going to talk about specifically in limits involving trig and some strategies that we can use there. The other concept that we talked about in this lesson was the different algebraic limit properties that we're allowed to use when manipulating functions, so long as both functions, or however many functions we're talking about, are continuous at the value that we are looking at. So write down any questions or post them below, and I look forward to supporting you on this in class. Thanks for listening.